In this lecture, we will study about the Laplace transforms. The Laplace transform definitions are shown here, but it's quite similar to a Fourier transform. In case of Fourier transform, the signal representation is a linear combination of this one. It means that we decompose the original signal in the combination of the exponential j omega t. The other way, this is the basis function for the Fourier transforms. What about the Laplace transform? In case of Laplace transform, we taking the basis function with e to the st. And here, the s include the j omega. So s consisted, the real part is a sigma and the imaginary part is j omega. So it's an extension of the Fourier transforms. In case of Fourier transform, this sigma is 0. In the Laplace transform, we take the sigma as 0, then it becomes the Fourier transform. In the S domain, here is S domain. In the S domain, basically, complex plane. Okay, so this one is a real axis, this one is the imaginary axis. So, in the Fourier transform, we use just only this imaginary axis. This axis is a imaginary part, j omega. But if we're taking certain point, then this will give a sigma and j omega. Like that. So by taking the basis of this one, we can make a Laplace transforms. Let's compare between the Fourier transform and the Laplace transforms. Here shows that the Fourier transform definition of xt. xj omega are expressed by xt times e to the minus j omega t, and take the integration the whole times minus infinity to infinity. This gives the Fourier transforms. What about Laplace transform? Laplace transform expressed by xs. At here you can think about s is real and imaginary part, okay? But the Laplace transform only take the imaginary part. So xt times basis function is e to the minus st. You know that this is basis function for the Fourier transforms, but the basis function for the Laplace transform is e to the minus st. And the s can be decomposed into real and imaginary part. Then it can be expressed in this way. So e to the minus sigma t come from the real part of the st. You know what? The e to the minus st equals to e to the minus sigma plus j omega. Okay, sigma plus j omega. And t. So this can be decomposed into two different factors. One is the damping factor. As time goes on, this will give damping. This was exponential decaying. As time goes to the positive, and the other part is minus j omega t. But this part, complex exponential part, is the same as a Fourier transform. So this one is shown here. So we just take the Fourier transform of this one. That will give the Laplace transforms. Fourier transform of this part are equals to the Laplace transforms. Then in somehow we can express that one into this way. You know what, that if we taking only the complex part, in that case j omega are expressed in that way. But if we take the s, then we can express that one into s. This is the s, okay? Complex plane domain. And in this case, at this moment, to think about between these two transforms, we already know the Fourier transform. But why do we need another transform such as Laplace? The reason is this one. The existence of Fourier transform is guaranteed by the delimited conditions. The later two conditions usually satisfy most of the signal, but some signal doesn't satisfy this one, absolute integral. It means that if we taking integration from the whole time by taking the absolute value of the signal, dt should be finite. This is the conditions. But some signal doesn't satisfy this one, especially for the exponential functions. Okay, e to the minus alpha t. If alpha is positive as time goes on, as a decaying, it's okay. But what about alpha is negative? Then it's exponentially growing. In that case, by taking integration, will diverge. It goes to the infinity. In such a case, Fourier transform does not exist. But if we take the Laplace transform, we can make it converge by use of these sigma terms. So certain sigma value make it, that this exponential growing signal can make it integrable. So in that region, the region means that the sigma constraint. If we give some real terms for this sigma value, then it converging. That is the definition of region of convergence area. So at this moment, think about it. Laplace and Fourier transform looks like twins, but the extended version is a Laplace transform, because Laplace transform can taking another factor. Is a real term can be existed. This real term make it converging. Some the non-converging signal can be make it converge. Okay, think about now the inverse Laplace transforms. We know that the inverse Fourier transform from this definition. Think about these definitions. We take the Fourier transform of this one. Okay, the Fourier transform of this one is this value. Okay, by taking the inverse Fourier transform, you know that we take the Fourier transform at here. So by taking the inverse Fourier transform, we can get the xt value. So inverse Fourier transform definition is this one: 1 over 2 pi x times e to the j omega t, taking the integration over omega. Okay, this one is the inverse Fourier transform. By multiplying e to the sigma t both sides, then xt is given in this way. Then we can using change of variable. Let's redefine s is sigma plus j omega. Okay, then we take the s value in that way. Then ds are given as a j d omega. Okay, so d omega are ds over s, ds over j. Okay, so d omega can be replaced by this value, and x s is given. You know that we take this one as s variable, and this one is this one. Then s will changing from minus infinity to, you know that omega changing from minus infinity to infinity, so this will changing from minus infinity to infinity to infinity. This is typo. So sigma minus j infinity to sigma plus j infinity is the range of the integration domain. So this is the integration domain from minus sigma j omega minus infinity to sigma plus j omega. So omega changing from minus infinity to infinity, and this j come from this factor. Then we can define the inverse Laplace transform. So we call this one is the inverse Laplace transform. So xt equals to 1 over 2 pi j, 1 over 2 pi j, and take the integration to whole range and xs times e to the st. This one is a basis function and over ds. So I talk about the meaning of this sigma. This sigma introduced to the unstable signal to make it converging. So this one is a arbitrary value that signal to make a signal converge. So that reason is called the reason for convergence. Okay, let's try to understand by use of example. First example is this one. Xt is defined as an exponential function. At this moment, let's think about that. Here is a time domain. It's defined only positive time. Okay, this is 0. So this one is defined. It depends on the a value. Depending on the a value, it can be diverge or converge. So whatever it's this one is an exponential function. By taking the Fourier transform, to be exist this Fourier transform, the a should be positive. Then we can take the Fourier transform. In that case, it's given in these equations. But we know that the unit step confine the integration range because t is less than 0. So all values are 0 due to this unit step function. So by make it 1 and take the integration from starting with 0 to the infinity, that gives this result. From here, by taking the integration of e to the minus a, okay, e to the minus a plus j omega dt, okay, omega t dt, with just the integration from 0 to the infinity, then it will give a plus j omega over e to the minus at times e to the minus j omega t, and another minus exists here due to this value, and the integration range is 0 to the infinity. Okay, so we use this one. Result should be this one, to be that one when we introduce the t with the infinity. Okay, it does, you know that complex exponential magnitude is always 1, so the important is this one. So e to the a times t, as t goes to infinity, it should be convergent. To satisfy that one, a should be positive. If a is positive, by introducing t with the infinity, it's 0. So this integration value is 0. So now we enter t is 0. Then it gives a plus j omega over 1. So we know that this one has a Fourier transform expression is this one, but we need another condition. That's this one. It should be satisfy these conditions. Okay. Now consider the Laplace transforms. In this Laplace transforms, we take the same xt, and the basis function is e to the minus st, and take the integration over whole times. But the same reason for the unit step, we take the integration from 0 to the infinity of the exponential function like that. But we know that s is sigma plus j omega t, so we can express that one into this way. In this way, it's the same reason. You know that by taking integration of this one, it will give this one minus a plus sigma t over minus a plus sigma plus j omega times e to the minus j omega t. And take the integration from 0 to the infinity. We can compare these two things. It's quite similar, minus and minus, e to the at, e to the a plus sigma t. This sigma introduced by this s, okay? S, the real part of the s is a sigma, okay? That is introduced here. And this j omega t is the same as this one. And the numerator, denominator are given here is a, but at this moment it's a plus sigma plus j omega. So when we replace the t with the infinity, it should be convergent. To satisfy this one, you know that the a plus sigma should be positive. Now it's changed. Okay. In the Fourier transform, this should be positive, but at this moment, a plus sigma should be positive. Okay. If it satisfies these conditions, then we can make sure that it's an infinity case it's a 0. It's converging to the 0 if satisfy these conditions. And now we replace the 0. Then it will give this value. Okay. Then sigma plus j omega is s. So we can rewrite that one into this way. But it should satisfy these conditions. Okay. Then in the real part of the s is a sigma. That should be greater than minus a. So this is called the reason of convergence. 1 over s plus a, and with the region of convergence is sigma is greater than minus a, then that corresponds to this function times ut. So this ut means positive going signals, positive time. Okay, or right-handed signal. Let's summarize that the Laplace transform of this exponential function. You know that as I talked to you that this one is a right-handed signal. It means that it's a signal does not exist at the left side. Only signal exists at the right hand side. Okay, because of this unit step function. So left-handed all the way 0. Okay, the Laplace transform is given as 1 over s plus a, and region of convergence should be defined in this way. Okay, let's consider another example. Here is, you know what, this one is left-handed signals. By taking the u minus t, it only exists at the negative times. Okay, positive time is 0. Okay, it's 0. So this one is obviously left-handed signal. Okay, this one is a left-handed exponential signal. Take the Laplace transform of this one. Okay, then due to these left-handed definitions, signal exists only negative times, minus infinity to 0 and minus e minus at times. Okay, we can drop this part because the integration range is limited already. So e to the minus st. Then we can do the Laplace transform in the same way. But you know what? S is sigma plus j omega. By taking the integration of this one, it will give a plus sigma plus j omega over e to the minus a plus sigma t e to the minus j omega t. And take the integration from minus infinity to 0. But at this moment, this minus is disappeared because of this minus part. You can compare with this one. So only difference is this minus signs. Okay, it's the same. The minus sign difference due to this one. Okay. Now the issue is this one. The convergence of this one corresponding if we replace time with the minus infinity at these times, it should be converging. In case of t is minus infinity, this should be negative now. Okay, that's these conditions. A plus sigma should be negative to converge. So this one defines the region of convergence. So if satisfy this condition, minus infinity case is 0. Now replace t with 0, then that will give 1 over this value. So if you replace t equals 0, this goes to the 1 and this goes to the 1. So it will give this result, sigma plus j omega. Only this part remained if this condition is satisfied. Then sigma plus j omega is s. So this is it. But the region of convergence are defined like that. So real part of s should be less than minus a. So let's compare these two things, this one and this one. You know that the Laplace transform expression is the same, but the region of convergence is different. Due to this region of convergence, one signal is a right-handed signal, but the other one is a left-handed signal. So Laplace, when you consider the Laplace transform, you need to also consider region of convergence also. Okay, the inverse Laplace transform depending on region of convergence. Okay, here shows the idea. The xs has the same expression 1 over s plus a. This one is also two different signal has the same Laplace transform but different region of convergence. Okay, one is greater than minus a, one is less than minus a. So by taking the inverse one, it gives a right-handed signal, but this one gives a left-handed signal. Okay, so the same Laplace transform with a different region of convergence gives a different signals. Here is the comparison. Region of convergence one is this part. Sigma should be greater than minus a. So this part is a region of convergence for this Laplace transform. So we consider both of the signal as a Laplace transform is 1 over s plus a. Okay, but one has a region of convergence with this pattern. Okay, this part is a region of convergence, then it gives a right-handed signals. But in this case, sigma real part of the s, this one is s domain, but the real part of s is less than minus a. That is the region of convergence. Then the inverse Laplace transform will give different signals. That's the left-handed signals.